All right. This worksheet 1 here over the fundamental theorem of calculus. Let's take a look here at example 1. All right, it says the graph of f of t equals 3 on the closed interval from -2 to 3 is shown at the right. So that's that. That's y equals 3, isn't it? Okay. A, shade the region bounded by the given curve, the x-axis, and the vertical lines, x equals -2, x equals 3. So that would look like that. Then you'd shade it in. Fill in the chart by calculating the signed area for each value of x using the geometric formula for area of a rectangle and properties of integrals. All right, so they're telling us here that capital F of x equals the integral from 0 to x of 3 dt. So in other words, what we have is the graph, little f is the derivative of big F. Does this look familiar? Okay, so when x equals -2, geometrically, we look down here, let's see. All right, geometrically, we've got the integral. I can't read that. For some reason, my copy didn't come off good. Let me rewrite this. Capital F of x, integral from 0 to x of 3 dt. We've got this, but that's from -2 to 0 is the way we always read it, right? From left to right. The area of that is 6, isn't it? Okay? But that would be the integral from -2 to 0 would equal 6. So, since it's from 0 to -2, it would be -6. Because when you flip the limits of integration, you can do that as long as you put a negative sign in front of your integral. We able to do that without actually writing it down? All right. Then when x equals -1, that's the integral from 0 to -1, right, which looks like that. But what I have showing there on the screen is really the integral from -1 to 0, which would be, well, from -1 to 0 would be 3, because it would just be the geometric area. So then the integral from 0 to -1 would be -3. Then when x equals 0, looks like that. Because there's not, I mean, from 0 to 0, you're not going anywhere. And what's the area of that? 0. Now we get into much simpler stuff here. Because now when x equals 1, that's the integral from 0 to 1. Well, the area of that region is 3. When x equals 2, that's the integral from 0 to 2. 6. From 0 to 3, 9. Then they want us to come up with a formula. Now, let's pretend that we didn't know how to do antiderivatives. Okay? Every time, wasn't our capital F value 3 times the x? 3 times -2, 3 times -1, 3 times 0, 3 times 1, 3 times 2, 3 times 3. So, it's 3x. Does that go along with what we know about antiderivatives? What's the antiderivative of 3? 3x. Okay, makes sense? All right. Ooh. Understanding took place? All right, well, good. Good. Sometimes those light bulbs flicker a little bit. All right, part C, graph the ordered pairs on the grid below. All right, so let's do that. So I've got -2, -6, 1, 2, 3, 4, 5, about right there. -1, -3, 0, 0, 1, 3. All right. Are they going to have us connect these? 2, 6, 3, 9. So something like that. And since our formula or our antiderivative is 3x, well, it should be a line, right? Y equals 3x. So mine's almost a line. So I've got that. And then D, write a linear function for capital F of x that represents the graph of part C. Well, we've said it a few times already. The formula is 3x, the antiderivative is 3x, but I guess I'm really not saying it right, am I? Shouldn't I be saying that something equals 3x? Y equals 3x, or capital F of x equals 3x. The equals needs to be in there. Equals. Okay? So either write y equals 3x, or better yet, to use their notation, which we want to do, right? You don't want to make up your own notation on the AP test. They won't count it right, no matter how right the rest of it is. They won't let you just change the letters. Okay? So capital F of x equals 3x. Well, what is, for part E, what is capital F prime of x? Well, we know that the derivative of 3x is 3. We also knew it from the way our function was defined. So even if we didn't know how to take the derivative of 3x, or it was just so complicated we couldn't do it, we can look right there with what I have circled and see that 3 is the derivative. Okay? So, in fact, let me rewrite that. Let me make that capital. I don't know why they're calling it F1 prime of x equals 3. Now, what's the point of an exercise like this? That's right. We're working with derivatives, antiderivatives. We're working with the geometric concept of area and integrals. Derivatives, antiderivatives, area, integrals. Oh, okay. That makes sense. All right. Is that enough to get you started? Okay, you want to go ahead and do number 2 as well? Well, hang on. Nope, we're not going through the whole thing. All right, example 2. The graph of f of t equals 3 is shown above. Oh, did I not copy everything off the worksheet, or does it expect you to look? I don't have a copy of the worksheet handy. They don't redo it. Let's. Okay. So I'm going to do this. I'm going to take a picture. Oh, it always goes over to the other screen. I should have remembered that. I'd finally gotten where I like Windows 7, and now every time when I open up Firefox on my computer, it shows up on the projector screen. It's like, why are you doing that? Okay, now I don't have a place to put it. So there's our graph. Refer to part A from example 1. All right, part A. What did we do for part A? Okay, we were shading in the region. All right. Fill in the chart by calculating the signed area of a new capital F equals the integral from 1 to x. What was it in example 1? 0 to x. Okay, so that is going to change a little bit, isn't it? Okay, so when x equals -2, so we started with this, and then we said when x equals -2, and we're starting at 1, we'll have that region, won't we? And the area of that region is a +9. But that's the integral from -2 to 1. We need to find the integral from 1 to -2. So the signed area then is -9 because our integral is written with the upper limit of integration being smaller than the lower limit of integration. Then when we have x equals -1, our actual area is a +6, but that's the integral from -1 to +1. We want the integral from +1 to -1. So it's a -6. Now x equals 0. So that area is a +3. But the area we want, since it's the integral from 1 to 0, is -3. And then x equals 1. That's what that looks like. There is no area. And then x equals 2. So now we're talking about that right there, +3. And it's the integral from 1 to 2 now, so we don't have to do any negative stuff, do we? And then 6. Okay? All right, now, what's the general formula? It's not 3x. 3x minus 1? Oops. 3 times x minus 1, or 3x minus 3. Why did it change? We moved the lower limit of integration. We moved the 0 became a 1. It ought to change, right? Okay. Now, well, they may lead us through this, so I won't say anything about it yet. All right. Part C, graph the ordered pairs on the same grid that we used before. So if we go back here, so it was what? -2, -9, -1, -6, 0, -3, 1, 0, 2, 3, 3, 6. Oh, they're just parallel lines, aren't they? Because they have the same slope. They both have a slope of 3. They just have a different y-intercept. All right, so we've got that. Write a linear function for capital F of x that represents the graph, and it says it should match the formula from the chart above. So capital F of x equals, and then I think I would rather write this as 3x minus 3, because it looks linear that way. All right, so what's the derivative of this capital F? 3. The derivative of the -3 is 0. The derivative of 3x is 3. So capital F prime of x is 3. All right, compare the two capital F's. How are they the same? They have the same derivative. They only differ by a constant. All right, like we said before, it's the y-intercept that's different. Remember, all these times when we've taken indefinite integrals, we've put that plus c, because you're going to have, because look, we had the same integrand in both problems. It was 3. but we came up with different functions that had a derivative of 3. That ought to seem normal to you, okay? If I had a capital F of x equals 3x plus 3, wouldn't it be in this same family of functions? Wouldn't its derivative be 3? Okay, so they're going to differ by a constant. That's what that plus c has been about this whole time. All right? So how are they the same? Well, I'll just show you what I wrote. F1 and F2 are linear functions with equal slopes. Thus, the derivatives are equal. You could have said F1 and F2 are the same except for a constant. They differ by a constant. And then a note to myself, remember, well, that's what the plus c is all about. All right? Make sense? All right, I think you can do this worksheet now, don't you? Now, can some of the problems get tougher and be different? Well, yeah. Okay, but I'm not going to work every one for you. I want you to either try them or retry them. All right. Now, on worksheet 2. They give us capital F, 12 times, written as a definite integral. Notice that every single time the lower limit of integration is a constant and the upper limit of integration is either x or an expression of x. They ask us to find the derivative. This is the second fundamental theorem of calculus. Okay? So, here's the way I started off. Well, let me put a screen up here. The simplest version of the second fundamental theorem of calculus is showing right there. If capital F of x equals the integral from a to x of f of t dt, the derivative of capital F, the derivative of the integral, equals the little f just in terms of x instead of t. Okay? So, in other words, number 3. We have capital F of x equals the integral from 0 to x of 2t dt. So 2t is the f of t. According to the second fundamental theorem of calculus, the derivative of that equals f of x. Well, if f of t is 2t, f of x must be 2x. Now, as I tend to do, I've over-explained that. It's real simple, isn't it? Whenever you have an x, whenever you have a function defined by an integral, and you have a constant for your lower limit of integration, and x for your upper limit of integration, the derivative of that function, the derivative of that type of definite integral, just replace the t with x. It's just trying to tell you that the derivative of an integral gives you the original function. Okay? So the ones where it's just an x for your upper limit of integration ought to take you all of 3 seconds to work. But the ones we need to get good at are the ones when the upper limit of integration is not x, it's an expression of x, it's a function of x. It's u. If capital F of x equals the integral from a to u of f of t dt, then it works this way. Remember, it's the chain rule. Capital F prime of x equals, all right, the derivative of capital F with respect to u times the derivative of u with respect to x. When we first learned it, it looked like this, dy du equals, or times du dx. It's just, they called it f instead of y, that's all. Okay? It's got an f instead of a y. But it's the chain rule. Now, here's the thing. D capital F du, the derivative of capital F with respect to u is just little f. Okay? So, this is the way to remember it. That capital F prime of x equals f of u times the derivative of u. So now we can do one like number 10. So let's ignore all this other stuff and look at number 10. We've got capital F of x equals the integral from 0 to the sine of x of 2t dt according to this right here. Capital F of x, capital F prime of x equals f of u times the derivative of u. So, if u is the sine of x and f is 2t, what's f of u? 2 times the sine of x. Times the derivative of u. What's the derivative of the sine of x? And that's it. And then maybe there's some simplifying to do. Maybe there's not. The only thing, I don't need the parentheses. Parentheses don't hurt anything either. It's okay to leave them. Okay? This ringing a bell? And again, we can make these complicated. But cutting to the chase, that's the way it works. Capital F prime of x. When capital F of x is defined to equal an integral with a constant lower limit of integration and a function of x as the upper limit of integration, you get little f of u times the derivative of u every single time when you take that derivative. All right? All right. All right, at the top of worksheet 3, let's look at this derivation of the first fundamental theorem of calculus. This is strange because they're saying from the second fundamental theorem of calculus, all right, the integral from a to x of f of t dt is capital F of x. And then as we discovered with, what was it, worksheet 1 from the fundamental theorem of calculus set of worksheets, that they differ by a constant, all right? We had a 3x for one of them. We had a 3x minus 3 for the other one. So don't forget the plus c, where capital F is an antiderivative of little f. Don't forget that the integral from a to a of f of t is going to equal 0, all right? Because geometrically, there's no region there to take an area of. So it would be capital F of a plus c, but it's going to equal 0. So that means that that has to happen. All right? Now, so that was when we, starting from here, that was letting x equal a. Well, now if x equals b, we can get that. And then here's, where am I trying to get to? I'm trying to get to this. Remember we talked about this yesterday? The fundamental theorem of calculus tells us that. We can solve that for, there's 3 parts. If we know 2, we can solve for the third. Okay? So I want to write it out again because I want to make sure that you're able to use this when it comes up. The integral from a to b of f of t dt, according to the fundamental theorem of calculus, equals this. So that's one thing, we already know it. You don't have to memorize these other 2 I'm going to write up here, but you need to be aware that they exist, right? If I add f of a to both sides, I get capital F of a plus the integral from a to b of little f of t dt equals capital F of b. And then if I subtract, so I've got it solved for capital F of b. Then if I subtract the integral from both sides, I get it solved for capital F of A. Don't memorize equation 2 and equation 3. Be aware that you can get them anytime you want, because you should remember that one. All right? Now, what I have highlighted here in yellow, accumulated, or sometimes it can be called accumulated change, or total change, or net change, is given by the definite integral whose integrand is the rate of change. Because derivatives are rates of change, right? They're slopes, they're velocities, but at their most basic, they're a rate of change. So whenever your integrand is representing a derivative, it's representing a rate of change. To find how much change there is, integrate it. Because what are integrals? They're accumulators. Integrals are accumulators. So if what it's accumulating is change, then it will give you the net change, the total change, the accumulated change. Does that make sense? If your integrand represents rate of change, then the integral measures how much change. The integral adds up the change. Okay? All right. So here's the kind of problems they're asking you to do here. Write this one down so you'll have an example to go by. The directions say to write a sentence to answer each of the following questions. If h of t is the rate of change of the height of a conical pile of sand measured in feet per hour, what does the integral from 0 to 5 of h of t dt represent? Get your units right. Okay? On a problem like this, and look, that won't be an entire free response question, but it might be part of it. Okay? You're gonna have to get the units right. All right, so h of t does represent change. It represents the accumulated amount of change. But now we got to stop just saying change in general. Change of what? Change of the. So if h of t is the rate of change of the height in feet per hour, then, so I'm just rewording what they've given me. Then, and now I'm stating the integral they told me to explain. All right, so I'm just kind of getting started, right? I'm gathering my thoughts. I'm getting this thing together. If h of t is the rate of change of the height in feet per, then the integral from the total, and I should have written in the total amount, I guess. The total amount of what? Change. Change of what? Height. Answering correct units. How's the height measured? In feet. So that integral represents the change of the height in feet. Go in total if you want. If I recall correctly, it's assumed you're talking about the total. Okay? Okay, now, we've explained the integral sign, measured the amount of change. We've explained why it's height, because that represents the change in height. We've written out that our units are in feet, because they told us it was feet per hour. That's where we got the feet. I've not used two things. I've not used the word hour, and I've not used the limits of integration. Well, can't the limits of integration be the time? Okay? We don't really think of that so much when we're talking about a pile of sand, but if our integrand was the velocity, wouldn't you expect the change, the total amount of change in position to be taking place in an amount of time? So same thing here. The total change in height is going to be taking place in an amount of time. So from hour 0 to hour 5. And then I rephrased that really more for you and I to understand here. That's the first 5 hours, okay? Because they're talking about a real thing here, right? Well, it can't have started piling up before time 0. And then if you go from 0 to 5, then that's the first 5 hours. All right? Does that make sense? All right, so you're going to do a few of those. You okay with that? All right. All right, on worksheet 4, we have some old AP questions. Let's take a look at number 82, which is the second one there on the list. All right, it says the following questions are from the 2003 AB exam, section 1, part B, calculator section. Yes. So it's multiple choice calculator section. The rate of change of the altitude of a hot air balloon is given by R of T equals T cubed minus 4T squared plus 6. For the interval from 0 to 8, which of the following expressions gives the change in altitude of the balloon during the time the altitude is decreasing? All right, now, if the altitude is decreasing, that function they give us, R is measuring the rate of change of the altitude. So if the altitude function is decreasing, the derivative of the altitude function, the rate of change of the altitude, has to have what sign? Has to be negative, doesn't it? Now, this is a multiple choice question. You don't have to write that down, but I think it's a good thing to think it. Okay? So, I need my calculator. All right, so let's punch in this function for y. All right, so x cubed minus 4x squared plus 6 and I'll graph that. I want to zoom out and be able to see more of that. Okay, so we got that. Now, our function, okay, our altitude is decreasing, so our derivative needs to be negative, and I just graphed the derivative, okay? So if I knew what those zeros were for where the derivative's negative, would I know what the limits of integration need to be? All right, so let's do that. Let's find one of them. So let's do second calc, zeros. So I can do the left bound there. Move the cursor over to the other side, do there. Make a guess. I get 1.5719. Okay, so it's either this. Oh, these are derivatives of my derivative. I don't want derivative of my derivative, do I? They already gave me the rate of change, so I can eliminate those right off the bat. That's it. It's A.